So this next lesson is on calculating instantaneous values. So in a DC circuit, when we did all the Ohm's law math back in first term, everything was constant, steady, straightforward. Okay, now as we move into doing the same thing in AC, because that's what we're working our way towards, is similar kinds of Ohm's law circuit calculations, and yet in an AC circuit where things are constantly changing, one of the things that we do is, or one of the things that we can do is freeze time, okay, and say what's happening at exactly this moment. All right, so remember now the voltage and the current is in a sine wave. Okay, and we have values within this sine wave. Okay, so the first value here might be V peak. Okay, there's a positive V peak, and down here we have a negative V peak. Okay, but in fact, when calculating Ohm's law, for example, we don't use the peak value of voltage. Okay, we use what's called, and I'm going to put it right in here somewhere, the RMS. So the RMS, or the root mean square voltage, okay, gives us a DC equivalent to AC. Now, I think, I'm pretty sure you would have covered this in first term. I'm sure Pete has gone over this with you. So the RMS value of voltage represents, and it's not an average of our sine wave, of course. The perfect average would be zero, right? Because the positive alternation perfectly cancels out the negative alternation. Okay, but we could turn this AC into a pulsating DC, either half wave or full wave, and talk about DC averages. Those are different than the RMS. The RMS is an equivalent value to produce energy. Typically we talk about producing heat. That is the output of a resistor. Okay, which is, RMS is 0.707 of V peak. Okay, but we have all kinds of other numbers here too, because the fact of the matter is the voltage is constantly changing, right? It's zero, and then it constantly climbs to whatever V peak is, and then falls back to zero, and then climbs negatively to our negative V peak and back to zero for a full 360 degrees. So a question could be asked, if I froze time at 160 degrees, so right there, let's just hit the stop button. And the question is, what is the value of voltage at that moment in time? Okay, that is what we're talking about when we talk about instantaneous values. Instantaneous voltages, if we're talking about the voltage sine wave, instantaneous currents, if it's current we happen to be looking at. But we're freezing time at some point along the sine wave. And when we talk about time, we talk about it in terms of degrees, right? I just said we're going to freeze time at 160 degrees, which is somewhere just before 180, okay? 90, 270, all the way to 360, which is back to zero. So when we talk about time, we talk about it in terms of where we are through the sine wave by degrees. When we freeze time at that moment, what is the value of the voltage at that moment in time? Well, a couple of videos ago, I told you that from this point on in the course, every time I say, how do you calculate that? The right answer is make a right angle triangle. And so that is exactly what we're going to do. Okay, right angle triangle will solve this for us. So here's the trick. Let's take this sine wave, this waveform, and what we do in the last video, I said, and we've done this for a while now, to simplify this rather complicated waveform, we're going to draw vectors. So let's back up a step. So, at a vector at 0 degrees, we have 0 volts. When my vector rotates to 30 degrees, It corresponds with a point on that sine wave. When I draw my vector at 60 degrees, I didn't quite get this to scale. We have a point, oh, that's pretty good actually. There's a point on our sine wave, and then when we get to 90 degrees, see if I can hit the spot. We're going to hit the peak right there at 90 degrees. Hey, that's not terrible. Okay, so here is, believe it or not, we're working our way towards a right angle triangle here. Okay, because at 30 degrees, okay, actually if we carry on, let's keep going for a second. Let's go from 90 degrees. If this is 120 degrees, we are back to that same level that we're at 60 degrees. And we move on to, where do I need to be? Sorry, that's not quite right. What is that? That's 120 plus another, that's going to be 150. And that should end up right there, which is not, so my 30 degree vector, the first vector I drew, brought me to this point on the sine wave. The 150 degree vector is at the same magnitude, but it's not there, it's over here, which looks like that's my 160 degrees. I said 150, 160. We almost landed in the right place, almost worked out for me. But we are drawing triangles here. Okay, let's pull out this 30 degrees. So if we were to ask the question, what is this magnitude at 30 degrees? We have a 30 degree vector right there, which represents that instantaneous point on the sine wave. So, sorry, making a mess now. 30 degrees, right angle triangle. But I don't have any numbers. Okay, for a right angle triangle, we only need two, right? I've got one, 30 degrees. I need the length of a side, and I can figure out all of my variables. Well, in fact, I do know the length of one of my sides. Well, I don't because I haven't put any numbers on here. But this vector, as it rotates through its 360 degrees, its direction is going to change, but the magnitude of the vector never does. The magnitude of each one of these vectors is, and we can see it at 90 degrees. The 90 degree vector right here lines up with V peak. So the only piece of information we need about our sine wave is its peak. And once we know V peak, we can determine the magnitude of any instantaneous point along the 360 degrees of the sine wave. Because every one of these vectors has that very same magnitude. And this vector at 30 degrees just happens to be the hypotenuse of our right angle triangle. The hypotenuse equals V peak. And then the question is, how high is this point from 0? If that's 0 volts right there, what is that height? And so that height is that point right there. And so this line on our right angle triangle, which is the opposite, equals V instantaneous. Okay? So we know the angle, because that's the question being asked. What is the instantaneous voltage at a particular angle? Okay? The only other piece of information we must be given is what is V peak, and that tells us what the hypotenuse is. And then we can calculate the instantaneous voltage at that angle, because that's the opposite of a right angle triangle. So what function utilizes the angle and the opposite and the hypotenuse? That's sine, right? Sine equals the opposite over the hypotenuse. So if the sine of the angle theta equals the opposite over the hypotenuse, we can do a little bit of algebra here. We need to isolate for the opposite. So opposite can stay right where it is, equals the sine of the angle theta doesn't move. Hypotenuse comes from the denominator on this side of the equal sign. Across the equal sign up to the numerator, it becomes times h. So the sine of the angle theta times h equals the opposite. So now I can make the statement, and this is my punchline and we're done, is V instantaneous. So the instantaneous voltage is equal to the sine of the angle theta. So whatever angle it is, we're asking the angle, what is the voltage, what is the instantaneous voltage at a particular angle, multiplied by V peak, because that's the hypotenuse of every one of these triangles. Okay, all 360 degrees around here, we can answer the question, what is the instantaneous voltage? The hypotenuse will always be the peak voltage. Okay, so the instantaneous voltage at 90 degrees is the peak voltage. The instantaneous voltage at 270 degrees is the negative peak voltage. Okay, the instantaneous voltage at 180 degrees is 0. Okay, but there's lots of points in between, and we can ask the question, and this equation will answer it for us.